logic. It is my pleasure to introduce José Martín Castro-Manzano. He is going to talk about Delenda as syllogistica.
Good morning. What I'm going to present, maybe, well, I don't know, maybe it is not that interesting because it's about syllogistics. Maybe for some of you, syllogistic is already dead. I don't know. But since the notion of contra-classical logic is gentle enough to include a wide range of topics, today I speak to you not so much about a contra-classical logic, but rather about an alternative proposal that goes against some common standards of contemporary classical logic. And to better introduce this proposal, I would like to quote Fred Sommers in a very recent book. In a very recent book, he was talking about his project, and he said that term logic will once again become the logic of the schools. And certainly, this statement is not only obscure, it is not only mystifying, but overly enthusiastic. But I will try to unpack what's behind it, so maybe you can find it interesting. So basically, I will present Sommers' term logic, and I will show why, as George Engelbrecht has put it, such logic is natural. Such logic is as powerful as standard first-order logic with respect to natural language reasoning, and it's also efficient. But further, I will also explore, or I will try to explore, in what sense such term logic behaves as a relevant logic or as a consistent logic. And also, I will try to show that it has a non-monotonic interpretation, it can be extended, and it's quite useful, especially for natural language reasoning. So, broadly speaking, I'm just going to remind you of some traditional terms. Then I'm going to talk about the typical critiques that are used to reject term logic. Then I'm going to present briefly Sommers' term logic, also known as term functor logic. Then I'm going to talk about some of the attributes of this logic, and if everything goes all right, I'm going to present some extensions, and then we'll conclude with some final remarks. Yes?
I think we should take it down because in the recording there are function of the lights.
Okay, then I'm going to take this over. So it's okay. So, well, basically, let me see if I have this here. Yeah. Well, we already know syllogistic, right? And we know that it usually depends upon the, 4 propositions or 4 statements, the so-called categorical statements, and the consequence relation is always well, it's some sort of necessitation, right? If we recall what Aristotle said, not only in prior analytics but also in the Sophistelenki, Aristotle uses the notion of necessitation, right? And that's a very important thing to note. And we know we have what a categorical syllogism is. We know categorical syllogism is just a relation between categorical statements. And we know this particular kind of logic is a term logic. That is, it depends upon the notion of a term, right? Every categorical statement is a relation of terms. A subject term related to a predicate term. And that's basically the problem, because that's usually the problem with syllogistic and the problem with any term logic. And perhaps according to Engelbretsen, it was Russell, the one who popularized the idea that the limitations of term logic are due to the treatment of propositions or statements as combination of terms, as pairs of subject term and a predicate term. And Carnap is famous because, well, among other things, because he generalized this idea to the whole corpus of syllogistic or traditional term logic, especially when he argued that the only syntactical option available in syllogistic is predicative, as in Socrates is mortal or every man is mortal. Right? So, conforming to this critique, the syntactical limitations of syllogistic show that term logic is unable to represent singular, relational, or compound statements, right? And thus is incapable of performing inference with such kind of statements, right? We cannot, so to speak, we cannot perform a relational argument, right? If I say something like, every colt is a horse, and a horse has a head, therefore some colt has a head, right? So that's a famous example. And we are also unable to represent compound propositions, right? It is kind of weird to talk about a modus ponens with terms, right? Or a modus tollens with terms. It sounds weird because a term is not a proposition. However, probably the hardest challenge for term logic is the assumption that the subject term and the predicate term are syntactically interchangeable, right? So, for instance, when we are using term logic, we can change the terms, for instance, in some sort of conversion. But that's problematic because, as each pointed out, that interchange between the subject term and the predicate term is problematic because the use of terms is unable to preserve the distinction between a noun and a predicate. Because if a subject is a term and if a predicate is a term, and we can change the places, then we have this strange notion that the subject becomes the predicate and the predicate becomes the noun. And that sounds kind of weird because predicates can be negated, right? But nouns, I don't know, it sounds strange. It sounds strange that the noun can be negated. Right? Thus, Gish would continue with this critique, and he would say something like this. An interchange between the subject term and the predicate term is logically impossible without a change in the meaning of propositions, for only nouns can be logical subjects in a given statement, but nouns cannot maintain their role as nouns if they can be converted into predicates. And this difficulty seems to doom not just syllogistic, but any term logic. And so Gish would say that between a term logic and genuine logic, he means first order logic, there can only be war. That's what he said. So let's go to war, right? So since the late 60s, Somers championed a revision and a revival of term logic in the face of Bargile challenge. I quote, "I challenge anybody here to show me a serious piece of argumentation in natural language that has that has been successfully evaluated as to its validity with the help of formal logic. I regard this fact as one of the greatest scandals of human existence. Why has this happened? Why has this happened? How did it come to be that logic, which, at least in the views of some people 2,000 years ago, was supposed to deal with evaluation of argumentation in natural languages? Has done a lot of extremely interesting and important things, but not this, right? And maybe this is because, as Woods has pointed out, because it is no secret that classical logic and its mainstream variants aren't much good for human inference, as it actually plays out in the condition of real life, in life on the ground, so to speak. And Woods continues, it isn't surprising. Human reasoning is not what the modern orthodox logics were meant for. The logics of Frege and Whitehead and Russell were purpose-built for the pacification of philosophical perturbation in the foundations of mathematics. Notably, but not limited to the troubles occasioned by the paradox of sets in their application to transferring arithmetic. Summers, however, closer to Aristotle, was rather troubled with how we think, not with the paradoxes of set theory. And I think that's an interesting point, because some of the challenge corresponds to this lack of representation of natural language reasoning. And Summers takes seriously this challenge. And for example, he asks something like this. What makes a rational agent realize that every colt is a horse and someone who owns a colt doesn't own a horse are jointly inconsistent? And he says, well, modern first-order logic, of course, is correct. Of course, is able to formally offer an answer to this question, improving that A and B are inconsistent. And that is something that traditional syllogistic couldn't do. And why is that? Because, of course, in first-order logic or in contemporary modern logic, we can interpret those statements and we can translate them into something like this, right? And we use quantifiers and we use variables and so on, but we are not using terms. However, if we want to prove that this pair of statements imply a contradiction, and if we use, say, some natural deduction rules, maybe we're going to need maybe 12 or 15 steps in order to see that actually that's a contradiction, right? However, such a process and the syntax of first-order logic is not that of the vernacular sentences in which we actually reason. And first-order logic deduction cannot serve as an account of our everyday reason. So, consider, for instance, the following. Right. Yes, of course, that sounds like inconsistent, right? But the question is why. And in this context, Summers wondered what would a cognitively sound logic be like? What would a loss of thought logic be like? And the result of this research program was term functor logic. And broadly speaking, term functor logic offers a plus-minus algebra that is able to represent, well, first syllogistic, but we are going to see that it can be extended in order to represent relational and compound proposition as well. And also it can be extended in order to represent more things, like like generalized quantifiers, for example. Now, according to this algebra, Sommer's algebra, so to speak, the 4 basic categorical statements can be represented by that syntax. And given that algebraic representation, the plus-minus algebra of this term functor logic offers a sound, complete, and simple method of decision. And basically, the rules is quite simple. It says that a conclusion follows validly from a set of premises if and only if the sum of the premises is algebraically equal to the conclusion, and that's a very important condition. And 2, the number of conclusions with a particular quantity, 0 or 1, is the same as the number of premises with particular quantity. Thus, for instance, if we consider a syllogism like this, which we know it's valid, we can see that the sum of the premises amount to the conclusion, right? All dogs are mammals, that is minus D plus A. All German shepherds are dogs, minus D plus D. And we sum the premises and we get the conclusion. Right? That's a very simple process, actually. As opposed to remove the quantifier, check if the variable is bounded or not bounded, then reintroduce the quantifier and apply, I don't know, modus ponens or whatever. This is actually way faster, right? And also the translation is way faster as well. And it's sound and complete. So, of course, I could say, well, it is finished because we have accomplished what we wanted, a term logic that is easy, fast, right? And it solves natural language reasoning problems. Yes, but that's only the case of syllogistic. But not only term functor logic is able to deal with syllogistic, this algebraic approach is also capable of representing relational, singular, and compound statements with ease and clarity while preserving the method of decision. So, for example, let us consider a couple of examples. This one right here, it's a relational statements, right? Some horses are faster than some dogs. Dogs are faster than some men, and the relation faster than is transitive. Therefore, some horses are faster than some men. And I want to do this because, as you can see, this is just as easy as taking out this and this. This is going to be minus f, right? And so this minus f is going to be erased with this one because it's a sum and so on. And the only possible conclusion is this one, and that seems very much like a linear logic, and that's another important thing of this particular syntax. But also we can reason with singular statements. Sommers has a particular theory of how to denote and refer, but let's just say, just for sake of this presentation, that in order to represent a singular term, we have to use a lowercase letter and a star. Right? And finally, for instance, this would be the representation of our response. But as you can see, the process is the same. We have the plus minus calculus, right? So we have minus p plus q. You get plus p. Therefore, the p's go away, and you get the q. So the addition of this syntax, well, I think it's good enough to answer the Carnap and Browser challenge that term logic cannot represent relational, nor singular, nor compound statements, because it actually can. Of course, provided some syntactical modification, right? But it can. But this one right here is a little bit. It's an example. I think it's more interesting. Because this one right here introduces this particular rule over here. The P is just like the introduction of a premise or the introduction of a hypothesis. So as you can see, the representation is quite simple. All universal statements usually have a minus sign, and in order to indicate their relation, we just have to use the subindex, and this notation over here indicates that what is acting upon. In that case, B is acting upon G, right? Because the boy is talking to the girl. So we can see, for instance, that by the application of the rule 23, this thing over here and this thing over here, and we just get minus G plus A, which is this actually right here, and the end that was right. And then we apply the same procedure with 4 and 5, and these things go away. And we get this over here, and we apply this with this one, and the G goes away, right? And we get the conclusion, which is every boy loves food. And if we try to do this particular reasoning in first order logic, maybe we're going to need like, I don't know, like 15 steps maybe, as opposed to 4, 5, or 6. No?
No, they're more or less the same.
They're more.
It's kind of a rotational variation, I think.
I don't know. I think this is way faster. We can.
Yeah, I think you're right. It is faster, but I don't think because of the numbers.
But we can try it. So the idea is that all this is good enough to respond to the problem posed by Rosen and Karna. But now let's go back to the example of how to explain the joint inconsistency, right? If we apply this term logic to the problem, we can actually see how this is faster, because after representing the statements, we can see clearly that we get the contradiction. Right, and Summers thinks that this example right here shows the virtues of this term logic, because it's closer to natural language reasoning. By contrast, the proof of this contradiction in first order logic would require not only a quantification translation, but many steps. And yet, the proof is doubly to cast light on why we instantly see the contradiction when an agent utters this couple of sentences. So, unlike first order logic, this particular term logic has some syntactical naturalness and is of reckoning, which Summers thinks are two essential features of a cognitively adequate logic that would cast an explanatory light on the celerity with which we reason with sentences of our natural language. This quick overview of Summers' term logic is, of course, I'm not giving all the details, but I think these examples show that term functor logic may be as powerful as first order logic with respect to natural language reasoning. Consider, for instance, another example like this. This is another example. If I say something like, Axel thought Martin, right? Something like Axel thought Martin, right? Therefore, Martin was thought by Axel, right? And how do we represent that?
T minus 1 MA.
No, well, but in fact, but this would be in first order logic, right? Something like this. Because, but this is kind of weird because the notion of active voice and passive voice is missing, right? In term logic, well, I have this quote from Frege. We naturally take a sentence in active voice as its passive transform to be different sentences, even though they share the same truth conditions. And Frege has held the same view, and on the basis of truth conditions, he dismissed the active-passive distinction. His claim was that since they express the same thought, the grammatical difference between them is of no concern to logic, right? So we cannot solve the problem, so it's not our problem, right? And well, I don't think that's the correct way of doing the things. But in term logic, this looks kind of awkward, but it represents the argument more perspective. It will look something like this, something like Axel. Right, and since the sum is commutative, we can, and right. Since the sum is commutative, we can say, well, then right, because the sum is commutative. But this relation over here, just by itself, is not commutative, right? It doesn't allow commutation by itself. We need some extra assumptions, and maybe those extra assumptions are not yes.
Just for clarification, but you don't want all relations to be commutative.
Yes, of course, not all. Yes.
So in the term logic, it's not built into the logic that they are. Is that right?
Yes, that's a good point. I think the only way in which we can block some commutation would be in the use of this non-perspective. But just with the plus, of course, we have a problem. Yes. We would have a problem if we just use the plus sign. Yes, of course. Yes.
But I thought you wanted to have like the active voice and the passive voice, right?
Yes.
And so A1 plus T12 plus M2, that means A thinks of B or A thought.
Well, let's use something like maybe it's because my English is as good as my Spanish. Because, I wanted to say thought, like from teach.
Oh, thought.
Yes.
All right. So A thought M, right?
Yes.
That's the active voice, and then the passive voice should be M was taught by A.
Yes, that would be it.
But you just swapped the terms, which would mean M taught A, not M was taught, but by A. I know words in Spanish, right?
Yes.
This is not in English, Spanish.
Yes, this maybe this is because I was thinking in Spanish.
No, but in Spanish it's the same problem.
Yes, in Spanish it would be like.
Has something on that?
Yes, because of the indices. Because
Yes.
I mean, M2 still holds the second place in the relation T. So I thought you put it in a different order.
Oh, I
see.
All right.
So that's the only thing. The only way I think we would be able to block those kind of problems. Sorry. So most of the troubles I'm making right here are because of my English.
So you're doing great.
No, I'm sorry. I understand now.
I'm being serious. Well, and we can find some other examples. One that I like is this one. I like this one in particular because I was working with Prover 9, and I wanted. Well, I don't have the screenshot, but Prover 9 told me something like this, like fatal error, unable to compute because you are using a two-place relation and you want to make this a three-place relation. Of course, it's going to fail. But for instance, this is an example given by José. He says something like this. Plato thought Aristotle with a dialogue. Therefore, Plato thought Aristotle. Something like this. Like Plato, something like Plato. Is this Aristotle with a dialogue? And those Plato. Is that right? Yes.
Yeah, so Plato taught Aristotle.
Yeah. Something like this. Right, and now the point is, of course, that we understand that in natural language reasoning, right? But if we want to translate this into first order logic, we will be doing something like this, like there is something, there's an X such that X is a dialogue, and Plato thought Aristotle with X, something like this, maybe. So, but the conclusion would look something like this, like Plato thought Aristotle, right? And that saying is kind of weird because right here we have a triplet relation and over here we have a triplet relation. However, if we think in natural language, that sounds kind of right. That sounds kind of right. I don't know if it's right, but if we apply term logic, we can see that these sort of problems, like moving from a three-place relation to a two-place relation, can be solved. So, for instance, here's an example. So, suppose a man loves a woman. What some men loves is a woman. The woman is what some men love. Oh yeah, this example comes from the assumption that this is the assumption. A man loves a woman, therefore some lover is a man. Right? That's the idea. And with this kind of representation, we can all of these follow, right? Just by applying some commutations or just by applying association, which we know are sound rules because the sum is commutative and associative. Right? And of this weird rule over here is called simplification, and that's a new rule that Sommer has proposed. Because I didn't tell you this before, but just as something like A implies B is something like this, something like A and B is something like this. So that's why simplification works with the sums. That's the reason we have it. All right, so by looking at these examples, again, this is just a quick overview of Sommer's term logic. We can see that with respect to natural language, not with respect to mathematical models or mathematical structures, this term logic is quite natural. It's as powerful as first order logic, and it's also effective. But also, it can be seen as some sort of relevant system or as some sort of a consistent system. That's kind of interesting. So this rule, well, not that rule. This rule over here, the rule donation, the donation rule, is the rule that takes a couple of terms and cancels out the terms that have opposite sign. And when we check the rules and when we perform inference in these systems, we can see that a valid reasoning modeled with this system contains the premises and only the needed premises for their validity and none other. So that's kind of interesting because that may account for some sort of non-monotonicity. Because if you add a new sort of premise, then you get something different. You don't get the same. And also, since a logic is linear when each premise is used just one time, and this particular rule works like that, then it's easy to see that this particular system is also linear, which is some sort of relevance, because we are only going to use the premises that we need in order to prove what we want to prove. But also, since these rules these rules allow for a condition of consistency in the premises. It grants that the famous rule ex contradictio sequitur quodlibet fails, for we can express contradictions in the premises, but nothing follows from a contradiction. Actually, that's kind of neat, because if you have something like maybe like minus S plus P, and that would be, say, all S are P, right? And you have the contradiction, that would be some S is not P. We would get something like this. Some S is not P. And they cancel each other out, and so we get an empty, we don't get anything, right? So even though we can represent contradictions, we don't get explosion. So it seems also then that this term logic has a paraconsistent behavior. And this is interesting because all these properties taken together, like the naturalness, the effectiveness, that it is as powerful as first order logic, and also it expresses some sort of relevance, non-monotonicity, and so on and so forth. Maybe this sort of logic is able to contribute to some sort of naturalized logic, and I find that interesting. So, having said all this, well, I was working on this, but still I find this like kind of I don't know. My Freudian paradigm is still inside of me, so I'm trying to find something more. So, for instance, something very neat about this system is that it can support extensions. So this one right here, for instance, is an extension of the additional syllogistic, right? This is an extension with extra quantifiers. This right here includes things like all, most, few, many, and so on, right? And this would be like the valid syllogisms, so to speak. So, but well, this framework over here was developed just by the use of distribution rules, by the famous rules of distribution. But we can apply Sommer's functional logic, and we can add just like some weird numbers just to get a new artifact. So this thing over here would say something like all S is P, right? This would say something like few. This is kind of weird, but this is not mine. This is mine, but this is not mine. Few S are not P. This sounds kind of weird because this is the positive fragment, but maybe later we can talk about why that thing is actually within the positive fragment. This would be most and many, right? And some, finally, right? And over there we have the negative fragment. So it seems that this particular system should preserve the properties of the original term logic. I'm not so sure about that, so we have to develop some sort of proof. But before I develop the proof, I would like to write down some examples. So, for instance, if I say something like, I don't know, maybe like, most logicians are friendly, which I think is false. Most logicians are friendly. Right? And I say something like, no logician is, well, no logician is ugly, right? So, what would be the conclusion of that? Notice that this, well, maybe some of you would say something like, well, like this is an E statement, right, in classical logic, right? And some of you maybe tend to say that this is an I proposition, right? But it is not, because I propositions are convertible, right? But this is not convertible. If I say well, if it was a particular statement, it would say some logicians are friendly, and thus some friendly people are logicians. But if we use the most, we cannot convert the proposition, right? Because we would say like, well, I like this example better. Most Americans speak English, but that doesn't imply that most English speakers are American, right? So this is not just as simple as right? But what would be the right conclusion? Thank you. What would be the right conclusion, right? Well, for one, we would need like some sort of alternative quantifier, right? Maybe like some Lindstrom quantifier, most speak quantifier, something like that. But we have this term logic right here, and maybe we can apply this term logic in order to find that. So basically, this would look like this. Most would be like most, I think, is number 2. So these things cancel out because of the same rule, and we get that the only possible conclusion is some friendly people are not ugly, because this is a negative, right? Some friendly people are not ugly, right? But that's the only possible conclusion. However, there are more combinations. There are all the previous combinations that I showed. Well, I wanted to develop the proof of this statement because I only have 10 minutes, so I'm going to move to the other stuff. I don't know why these things like this. It should be in the right direction. I don't know what happened.
Press Command R.
Command R.
No.
Well, I can explain that anyway. So we've been working in this term logic, and we are looking for the possible application of this term logic, because I think that one of the virtues of this sort of logic is actually that it can be directly applied very quickly. So one of the applications is, of course, the use of generalized quantifiers. Thank you very much. But another use is, of course, in diagrammatic reasoning, which is something that I'm exploring right now. So this is actually a work from one of my students, Roberto Pacheco. For instance, if I say something like the previous, well, no, I'm going to use an easy example. Say I say something like this, like all M are Q, and I don't know, again, many, right? Let's say many S are M, right? So if I apply some term logic, and if I apply this sort of modification with the extra quantifiers, I'm going to obtain the right conclusion. But we can also have a diagrammatic representation of this thing right here. We would say all M is Q, right? And that's quite evident. Everything that is M is also Q. And many N's are M. Would look something like this. but the many statement requires at least one circle over here. So the only possible two conclusions I can draw from these statements are many SRQ and some SRQ, which are actually drawn over here. So the system is well behaved. And and the last application that we are developing right now, that's done by my student Ignacio Lozano. We are developing some sort of alternative prologue, right? We are developing some sort of Aristotelian databases, but not with the syntax of prologue, because the syntax of prologue assumes first order logic. But we are applying this sort of plus-minus calculus, right? And well, I had to rush at the end, but I just wanted to conclude with the following. To wrap this up, Summers' logic is not precisely contra-classical in the sense that it validates schemes that are classically invalid, but it is contra-classical insofar as it rejects the classical syntax and the classical deductive base, while it provides a natural system that is as powerful as a standard first-order logic with respect to natural language. But it is also relevant, very consistent, and extensible, and of course useful. Right? So in other words, it looks kind of promising. I think I still have work to do. So after this quick overview, if we ask whether we should forget term logic or syllogistic, I think not. I think we have a lot of things. Thank you very much. Yes.
Give me a second.
So I thought that was very interesting. I don't know a whole lot about that stuff. So it was interesting, and I think it's interesting in its own right as something. But as a response to the Russell complaint that you read or told us about, where Russell was saying, term logic just can't do enough. It seemed to me that this approach almost concedes the point, but then makes things worse. Okay? So it concedes the point because it did become pretty clear that this is just a sort of change in notation from the standard first order. So it sort of concedes the point that you need the first order structure.
Yes.
If you want to write it in this notation, fine. This notation, as you've said, has some virtues in terms of if you know elementary arithmetic, you might be able to move faster or something. And that's something. But as an account of sort of logic, sort of, if we're thinking of that as sort of universal, part of all our theories and all that, it seemed to me that this goes in a bad direction by building in too much. So my initial question about whether you get commutation through not, I mean, that should be part of a theory. And your example from Aristotle taught Plato with a book, therefore Aristotle taught Plato. You're right, that's a consequence. The one's a consequence of the former, but not sort of a logical one. Instead, it has to do with assumptions we're building in about, and so on. So I guess 2 points. One is, as a response to Russell, I think it concedes the point. And but as an account of logic, at least on one account of logic, I mean, it goes too far. It sort of builds in too much theory. So, right.
Well, I don't know what to say, but I think I agree in general terms with your observation. Maybe I would have to distinguish maybe like two sort of levels of analysis, because of course I agree with you that this thing seems like a lot more work, and seems like it requires some extra assumptions that maybe are not that transparent. And I agree with that, but for instance, when I at that level, I agree with that. But for instance, at the level of the application of the system, I really think this system is way more faster. For instance, because of the numbers of the rules. Of course, the rules depend upon the notation, right? Right. I find it ingenious. That's maybe why I'm being struck by this notation. Because I find it very useful, especially for some sort of naturalization of logic, right? So since I'm interested in naturalized logic, that's why I feel that, yes, it concedes the point, but not in a negative way, right? Maybe like in the apophatic tradition, like by via negativa, right? Something like that. I don't know. I have to think about that. Thank you very much.
Thanks.
Thomas.
Oh, so question/comment.
Yes.
I should have anticipated, right, that you were going to bring up existential import at some point, because that's a property of traditional syllogism that is, actually contra-classical. And I wanted to know if you had any thoughts about that property of traditional syllogistic, and if you did have any thoughts, I wanted to comment that Storrs McCall did a bunch of work on Aristotelian syllogistic as a sort of contra-classical notion. So the question is, have you thought about existential import? Does it play any role? Is there a way to permute this stuff to accommodate it and so forth?
Yes, there is a way to accumulate it, of course. If you ask me, I don't like existential import, but and this system actually the notation is actually incorporating the rejection of existential import. So, for instance, of course, if we have something like minus x plus b, which would be like for all x, something like this, we don't have such thing as subalternation, right? Because you cannot get the plus from the minus, right? But for instance, once we are reasoning, you only have to add the existential import as another premise, and you can deal with existential import. But if you ask me, no, and I don't like it as well. So. But thank you very much.
Okay, I want to start by challenging that it is actually easier, because it's not actually. I mean, the thing is that the proofs you showed us are you kind of cheated, because actually a lot of the work is done before you can start drawing, right? So can you put up the one about the colts and the horses?
How do you do that?
Yeah, that one. It's you put it. Oh, it's very easy. Look, just 2 steps. But of course, it's not just those 2 steps, because if we just look at the first premise, I mean, how do you know that you have to represent every call support that way? Because as you showed us, every call support can be represented in a lot of ways. It can just be minus c plus h. It could be minus c for whatever index plus h for that same index. So yeah, we know that is the right representation in order to get the proof.
Yeah.
But in order to get there, you should have gone first through the universal minus c plus h, and then instantiated into minus c2, and then you would have to know that it had to be 2 and not 1, because if it's 1, the proof doesn't work. So actually, there's a lot of work in the representation that makes it at least as hard as just first order logic, at least for this kind of examples.
Yes, I understand the observation, and I understand the objection, but I don't think but I don't think it's strong enough. For one, well, I don't want to sound like I'm in the defensive, but I'm going to
defend it.
Because, of course, that the same objection can be done to this. For instance, I have students, and I some of them, not all, but I'm starting to teach this notation with them. And then when I show them the alternative representation in first order, they say, well, that's way more complicated. That's actually way more complicated because you have to understand the notion of quantifier, you have the notion of bounded and free variable, and so on and so forth. So,
okay, so maybe it's not as complex as first order, but it's definitely more complicated than you were trying to.
Maybe, of course, because I'm a propagandist, so logical propaganda already. So, yes, of course, but the notion of this representation is that once you take away quantifiers and variables, you take away all the
You're not taking variables. I mean, those indices are variables.
Yeah, exactly.
Yes, I mean the notion of variable as the x, the y, and so on and so forth. Because of course, I'm using variables. Of course, yes. But maybe it would be more precise if I say we're taking away the notion of the quantifier, the bounding variables, and so on and so forth. But yes, yes, I don't know if I answered the question.
No, yeah, you go.
Well,
Something.
thank you. No, thanks to you.
Can you go more slowly about the links between this and the non-monotonicity?
Yes. No, just I want to check out my notes because sometimes, especially when I'm being recorded, I say things and then I regret what I say. But the idea, broadly speaking, is that wait a second. Well, for instance, once we have a translation of a particular piece of reasoning, and we apply these rules, this logic behaves kind of with some sort of minimal conditions, and that is that the premises that are not used are not required. So every possible conclusion that you draw is obtained from that set of premises and only that set of premises. So when you add new information, if that information is relevant, you are going to change the conclusion. Or if that information is inconsistent with the premises, you are going to detach some sort of empty set, so to speak. So that's why we say it. I'm not saying that it is non-monotonic per se. I think it has a non-monotonic behavior.
That is sensitive to the context.
Yeah, exactly. Yeah. But I don't know if that answers the question.
But you don't have something like negation as failure, right?
No.
Just unification of the
No.
different parts in terms of plus or minuses.
Yeah.
Okay.
Yeah, this is related. I'm wondering about some of the, so you said like when we have contradictory premises, they cancel out and we get nothing.
Yeah.
I'm interested in the case of contrary premises, because it looks like you do still get some very strange conclusions out of there, right? So from all horses are happy and no horse is happy,
Yeah.
right? The horse bits stay, they're both negative.
Yes.
The happy parts cancel out,
Yes.
and so you get no horse is a horse. Or from most horses are happy and most horses are not happy, right? Again, the happy now cancels out and you get some horse is a horse. And so, I mean, there's an appeal to the simplicity of just adding these things up.
Sure.
But I sort of can't help but wonder, are we really getting at everything we want to get at here? Like, is this, I don't know what I should conclude from contrary premises, right? I mean, maybe there's argument to be had about what to conclude from contrary premises. But these don't seem like the kinds of things we would want to conclude from contrary premises. I mean, surely the options are like everything, nothing, the premises themselves and what follows from them individually, right? I mean, something like that. These sort of very strange results seem like sort of artifacts of oversimplifying the system, maybe. Yes. I don't know, I mean, what's your take on these sort of
Yes, no, I agree. I agree because at the end, as I said, this system right here is actually very classical at the end. It is not classical, not in the same sense as other types of logic. It is just not classical in the sense that it has no respect for the Freudian paradigm, right? With respect to the syntax and with respect to the natural deduction rules of the axioms and whatever.
But it also has no respect for natural language syntax either, right? I mean, it has this very strange, sort of real spinny kind of syntax.
Yes, yes, I agree with that, right? The idea is that I think the idea of Summers is that we can reduce all that stuff into some sort of basic arithmetic, right? So if we are familiar with the plus-minus signs, plus some other
the particularity stuff matters too, right?
Of course, yes.
Things
So,
can
yes.
be synonymous that shouldn't be synonymous.
Yeah, so yes, I find well, for instance, the other day I was looking from some particular inference, right? And I was performing inference with the system, and I reached a conclusion that I didn't see coming, right? So I was wondering, am I wrong? Is the system wrong? Are we both wrong? So I turned out to good old first order logic, right? And I said, well, I don't trust in myself. I'm going to use my theorem prover, right? And actually, the theorem prover said that that was an invalid inference, but it was valid in this particular system, right? So that's also kind of weird. I have to check into that. So there are some caveats there. So I have to figure it out, right? But yeah, thank you. And that's kind of weird as well because I'm trying to evaluate this logic with the other logic, right? So that's, but I don't know. Maybe that's because I don't have more friend logicians over there where I have. My only friend is my computer.
Just quick, what's the Freudian intuition again?
Well, yeah, that's a good question. Summers published an article, I don't remember right now when, but the article is called On a Freudian Dogma. And the idea is that the assumption that particular singular statements and universal statements have different form. He thinks that that's because we have the assumption that sentences are a combination or a composition of a noun and a predicate, or a function and an argument, so to speak. And Summers believes that actually that's the assumption that makes first order logic unable to deal with natural first order logic. That's more or less.
So just quickly, the only reason I ask is that I can't help but think, I'm not a Frege scholar, but I can't help but think that it was really important to Frege that logic be formal, as sort of bare of assumptions as possible.
Sure.
And so, and again, it just seems like there's so much more built into this that you're deviating from whatever the definition of formal is. It looks like you're deviating a lot from it, building a lot more into this system. Anyway,
Okay. No, I agree. I actually agree because this thing over here doesn't look like really a formal logic. It almost looks like some sort of, I don't know how to say it.
Shorthand or something.
Like I was about to say like heliomorphic logic, right? Like some sort of. I think there are a lot of material implications of it. Well, not material implication in the sense of material implications. No, there are some material assumptions behind the notation, and I think that accounts for the effectiveness of the system because actually that notation is coupling, is dragging a lot of assumption. So that I think is why this thing works, and that's why I think you see this as fishing, right? Because the notation is including a lot of the inferential power already. Well, I don't know. Thank you.
I know we've been saying that this seems closer to a notational variant of first order logic and things like that. But it seems to me, I don't know, this is the first time I see this kind of things, and this is just like very fast intuition. But it seems to be very, very close to sequent calculus, because the minus are the things that are to the left, and the plus are the ones that are to the right, and then actually you get more or less the very same rules. Have you explored it, or have people explored this relation?
As far as I know, no. And I haven't explored that yet either. So
yeah, because it does seem a lot like
I have to check into that. Right now I'm worried actually in that sort of application, but I have to look into that. Sure, thank you.
no, thank you.
I've got a question. So
Sure.
I'm not sure I'd be very happy to go with this logic, because I think that we want logic to help us, I mean, among other things, but mainly to help us draw conclusions from a certain set of premises.
Yes.
And here you're just limited to some things that follow. I mean, I would say that logic has to do with truth preservation, right?
Yes.
And here it's a little bit less. Well, not less, but on the other hand, have you explored? So I think this would be really useful as a hyper-intentional logic, or for instance, to talk about aboutness, to analyze certain things in that direction. Have you?
Honestly, not. The most recent thing I was looking into was the notion of the generalized modifier. So I have to look into that. And I have another issue, for instance. I also have the issue of how to represent, of course, intentional logics. Because, I don't know, some days I feel like I like S5 and S4, and right, sometimes, some days I'm feeling modal. So I have to look, for instance, into that. How can we extend this into some other kind of logics, like intentional logics or whatever? And I don't know, I have to check it.
But what I mean is rather, you know, these logics are super fashionable now, that like, the idea is that there's some intentional predicates or hyper-intentional, right? Like for instance, I know hyper-intentionality rate means that the predicate is a predicate of formally or synthesis or even an operator, it doesn't matter. And then even if two sentences are logically equivalent, you cannot assume that because one satisfies the predicate or the operator applies to one, it also applies to the other.
Sure.
And here I think, so basically what a hyper-intentional logic is the internal logic of such predicate or operator.
Sure.
And this one, it seems to be a good candidate. One such predicate would be aboutness, right? So I think that here a sentence is about something, doesn't mean that all the sentences that are logically equivalent to that one are about the same thing, but maybe in this logic it does.
I have to check into that as well.
Right? And then this sounds to me like very reasonable, I would say. I don't know.
I don't know either. I have to check that out. But thank you very much. I'm going to take into account of those comments.
Someone else? Okay, then I have this very small thing, which is, so you talked about simplicity, and there was this idea that, well, I mean, it's not really that simple, but I think there are two things at play here. One is the syntax, and the other one is how to find out whether an argument is valid or not.
Sure.
Right? And the syntax is simpler, I think. And how to find out whether an argument is valid or not seems like really simple. It's just a sum, right? But I think that this doesn't necessarily mean that how to find out whether an argument is valid or not is simpler than the case of first-order logic, because you've been comparing it all along with natural deduction.
Sure.
Calculus, right? But well, we know there are different ways of
Sure.
doing this, right? We could also go semantically, or
Sure.
there's also game theory,
Sure.
right? And nothing precludes the possibility that we devise a nice system, semantic system or game theoretic system that is as simple as this one, right?
Sure.
For first order logic, for at least certain fragments of first order logic, in particular the ones that you can
Yes.
emulate here.
Yes.
So syntactically it's simpler, but I'm not sure whether it's also simpler in this other sense.
Yes, I agree. I also don't know. And as most comparative studies, I think that we require, well, I don't know if, yes, well, I'm going to say like this. Since the idea of this sort of logic is to provide a cognitive apparatus to develop inference, I think we should compare, cognitively speaking, so-called rational agents performing inference tasks. We should measure which one is actually more efficient, so to say. So right now, I think it is way more simpler because of me, because I'm performing inference really fast and really quickly, right? But I'm not the measure, right? I'm not the metric. But I think if we are going to do some sort of comparative study in order to determine whether it is faster or easier so we would have to look into computational complexity for one, and we would also have to look for how easy it is for a rational agent to perform inference. Like, I have to
How does the simplest algorithm
Yes,
look
exactly.
like if there's such a thing?
Yeah.
Right. And for a particular fragment.
Exactly, of course, yes, completely, I completely agree. Right now, this student of mine that is developing this algorithm, I don't know what he's doing, but the other day I saw his code, and he had like 4 loops. So that's not really efficient, right? But I have to look into that in order to maybe provide a more sensible answer to that.
No,
to that.
thanks.
No, thank you.
I think, yeah, we have 4 minutes. Someone has a question? No? Otherwise, thank you very much.
Well, thanks to you.